Good day everyone. I am Joshua Mercado from Electronics Engineer 3rd year section 2. I am now discussing the topic force between differential current elements. The concept of the magnetic field was introduced to break into two parts the problem of finding the interaction of one current distribution on a second current distribution. It is possible to express the force on one current element directly in terms of a second current element, without finding the magnetic field. Since we claim that the magnetic field concept simplifies our work, it then behoves us to show that avoidance of this intermediate step leads to more complicated expressions. The magnetic field at point 2, due to a current element at point 1, was found to be d h sub 2 equals to I dl sub 2 cross product A r sub 12 all over 4 pi r sub 12 squared. Now, the differential force on a differential current element is dF equals to IDL cross product B. And we apply this to our problem by letting B be dB sub 2, the differential flux density at point 2 caused by current element 1. By identifying IDL as I2, DL2, and by symbolizing the differential amount of our differential force on element 2 as D quantity D F sub 2. Now we have the equation D quantity D F sub 2 equals to I sub 2 DL sub 2 cross product dB sub 2. Since dB sub 2 equals to we obtain the force between two differential current elements, D quantity D F sub 2 I sub 1 I sub 2 over 4 pi r sub 12 squared dl sub 2 cross product with dl sub 1 cross product A r sub 12. Now we have a sample problem. As an example that illustrates the use and misuse of these results, consider the two differential current elements. We seek the differential force on dl sub 2. We have I sub 1 dl sub 1 equals to negative 3 ay a dot product m at p sub 1 5 2 1, and I sub 2 dl sub 2 equals to negative 4a z a dot product m at p sub 2 1 8 5. Thus r sub 12 equals to negative 4ax plus 6ay plus 4az, and we may substitute this data into equation df sub 2 into this equation, and we have df sub 2 equals to 4 pi 10 to the negative 7 over 4 pi negative 4ax cross product negative 3 ay cross product negative 4ax plus 6ay plus 4az all over 16 plus 36 plus 16 raised to 1.5, and we have 8.56 ay nanonewton. Many chapters ago, when we discussed the force exerted by one point charge on another point charge, we found that the force on the first charge was the negative of that on the second. That is, the total force of the system was 0. This is not the case with the differential current elements, and df sub 1 equals to negative 12.84 az nanonewton in the example above. The reason for this different behavior lies with the non-physical nature of the current element, whereas point charges may be approximated quite well by small charges. The continuity of current demands that a complete circuit be considered. This we shall now do. The total force between two filamentary circuits is obtained by integrating twice. F sub 2 equals to I sub 1, I sub 2 over 4 pi surface integral d L sub 2 cross products surface integral d L sub 1 cross product a r sub 12 over r sub 12 squared. And we have this equation is quite formidable, but the familiarity gained in the last chapter with the magnetic field should enable us to recognize the inner integral as the integral necessary to find the magnetic field at point 2 due to the current element at point 1. Although we shall only give the result, it is not very difficult to make use of this equation to find the force of repulsion between two infinitely long, straight, parallel, filamentary conductors with separation d, and carrying equal but opposite current I. The integrations are simple, and most errors are made in determining suitable expressions for a r sub 12, dl sub 1, and dl sub 2. However, since the magnetic field intensity at either wire caused by other is already known to be I over 2 pi d, it is readily apparent that the answer is a force of over 2 pi d newtons per meter length. That's all. Thank you. I hope you enjoy.